Hello friends, I Professor Gaurav Murghare welcomes you all. Today's topic of discussion is the discrete time Fourier transform DTFT and discrete Fourier transform DFT. So let's proceed with the lecture. So discrete time Fourier transform, which we usually call as the DFT, is periodic with the halving of period 2 pi. It is denoted by the formula of x of n. Here the x of n is a discrete sequence. We all know about the Fourier transform. So Fourier transform for normally used for the continuous signal, but the discrete time Fourier transform is used for the discrete signal. Although it gives us a continuous output, but the input was a discrete signal. So xn e to the power minus j 2 pi omega into n. But we are taking the discrete signal, so instead of integration, here the formula of the summation from minus infinite to plus infinite. X of omega is also commonly denoted by x of e to the power j, because this e to the power minus of j 2 pi omega n is the multiplication factor for our DFT formula. It is also having the periodicity. So x of omega is the representation of any xn signal in the frequency domain. So whatever the frequency component present in the signal xn, whether it is a combination, xn is the combination of multiple signal or a single signal, it will give us all the frequency component in the continuous form if we are going to use the DTFT or the discrete time Fourier transform formula. Similarly, the inverse discrete Fourier transform can also be calculated, but the only thing is, instead of using the positive multiplication factor, here the multiplication factor e to the power minus of j omega n, that means positive of j omega n is used, and 1 upon 2 pi is multiplied with this. So here an example is showing. So if we'll substitute any delayed, that means del of omega minus omega naught is the delayed impulse, so we will be going to get a output of e to the power j omega naught for the signal. For the DTFT, there is an important property of the convolution property, or which we also called as the multiplication property. As we all know that any two signal, if normally multiplying in the time domain, it's not the multiplication, it's actually the convolution. So in the slide, if you see, xn is one signal and mine is the other signal. If we'll normally linearly multiplied it, so this is not a multiplication, it's a convolution, and we have to use the convolution formula. So if we'll convolve any two signal in the time domain, it is having the multiplicate, that means if we'll convolve any to time domain signal, it will be linearly multiplied in the time domain. Similarly, if we'll convolve any two signal in the frequency domain, then it will be linearly multiplied in the time domain. Only the difference of 2 pi is multiplied in the first case. Now we'll take a look about a rectangular window and its transform, basically the discrete time Fourier transform. So for the Fourier transform, we have calculated for any rectangular pulse. Here we have taken as a discrete rectangular pulse from minus 5 to plus 5. It is having the impulses or the train of impulses of 1. So any signal is multiplied with this signal, then the output will be going to get only for the duration of minus 5 to plus 5. So this is a rectangular window function of value 1. So if we will calculate in frequency domain answer, that means Wn is the signal we have taken, and W of omega if we have to calculate, the answer is coming out to be sine of 2n plus 1 omega by 2 upon sine of omega by 2. So it is a function of sampling function or sinc function sine t by t. So its representation or the spectrum in the frequency domain is like this. That means it is having the maximum value at the center of the value. This is the frequency. Now this is the time domain signal and this is the frequency domain signal. It is having the maximum value in the time domain and not used to say that 90% of the energy was stored here, and it will be going to decay up to the higher value or at the value of infinite. Next, as we all know that for the continuous signal from minus infinite to plus infinite, we can calculate by using the DTFT, but it is a very difficult process because for the value in the discrete time we have having only the value of finite sequences. So we will use a practical situation or the practical tool which is called as the discrete Fourier transform. In the discrete Fourier transform, it is limited to the finite sequences from 0 to n minus 1, and if we require the n number of samples and suppose n minus 1 sample is given as, we can add the 0 in it, so we called as the 0 padding for this. So formula for this signal is n is equal to 0 to n minus 1. In the DTFT the formula was minus infinite to plus infinite. Here the limit was n 0 to n minus 1, where n is the total number of sample in the given time domain signal. Instead of multiplication factor e to the power minus j 2 pi omega n, here the factor 2 pi k instead of omega was put here. So what we will be doing, we are taking 2 pi of k upon capital N instead of omega, where omega is the frequency, k is the samples with the same value 0 to n minus 1 for the frequency samples, and capital N is the number of sample. This x of k is also called as the DFT coefficients. So inverse of DFT can be also calculated by the formula, only the difference is being that here we will use the positive formula, we will use the positive e to the power plus j factor, and 1 by n is divided for this. So if we'll see, it is also having the periodicity property, so n number of sample is added in the action signal will give the same sequence. So for the DFT the signal is having the periodicity property. So even though we start off from a periodic signal, the inverse transform is the periodic signal. Similarly for if we'll instead of using the inverse transform, if we'll using the DFT for the periodic signal, then will leads to the or reaches to the periodic signal. Make sure the fundamental period of inverse transform should be equal to the original or periodic signal for that. Now the sample DFT will check it out. So sampled version of DTFT, that means if the DTFT we have taken the samples of the DTFT, we simply get the DFT value. So as I already told, for the DTFT is for the continuous sequence, while as the DFT is for the finite number of sequences. So in the last, we will just discuss about the differences between the DTFT and the DFT. So DTFT we normally use for the infinite, as for some cases we can use for the finite sequences, whereas the DFT is used only for the finite sequences. These are the first difference for there. So second difference, the DTFT is the theoretical. It is very difficult to practically implement this, but for the DFT we can use practically, and normally it is used in the computers. DTFT is derived from the DFT. DTFT is having a periodic and a continuous signal with the time period of 2 pi, whereas the DFT is non-periodic, non-continuous, so it is not having any periodicity. It will give us the higher number of frequency component, whereas the DFT give us the lower number of frequency component. It is the accurate, but okay, not physically realizable. So it is physically reliable, but we have to take more number of samples to get the accuracy. And the formula for the DTFT and DFT we have already discussed in the previous slides. So I hope you all have understand this lecture. Thank you for attending this session. We will back with some new topic. Thank you.